So we're starting Unit 3, which is on electric, gravitational, and magnetic fields. This will be a very scratching the surface introduction to field theory, which you'll study a lot more in university. And we will start by looking at gravitational fields, and then we will look at electric fields and then magnetic fields. This unit's kind of split into three parts. With gravitational fields, we'll be studying that and doing a quiz shortly after we do the 3 lectures on that. And then we will look at electric fields, do a quiz on that, and then magnetic fields, and kind of bring it all together with a quiz on magnetic fields, and then finally a test on the entire unit. So there's quite a bit to learn here, and we'll get started. I know on your formula sheet some of the equations may not be there, or they may not be in the correct spot on the formula sheet. So make sure that you're aware of where those equations are. And for example, the main equation in this lecture, which is the equation of universal gravitation, is found in Unit 1 on your formula sheet. Now, universal gravitation, or Newtonian gravitation, is covered in section 6.1 on your textbook. So we'll just in case you want to follow along, but I will go through this lecture and explain basically what it covers in that section. Now, one of the things about gravitation that we should consider is that gravitation is the weakest of the fundamental forces, yet it's so powerful that it actually formed these large structures called planets and stars. It forms the galaxies. It defines the movement of the stars and the galaxies. So if you're not aware of how a planet or a star forms, the basic idea is that particles, whether they are the gases or rocks, have a gravitational effect, and they attract each other. And as they kind of attract each other, they start to get closer and closer together. And once we have a larger mass of particles, they start to, the pressure on the particles that are in the center of that mass starts to form a core because of all the pressure of the other mass that's pushing, that's basically crushing it. So gravity, of course, it is the weakest fundamental force, but it's this force that also has the ability to create stars and planets and define the movement between those. So that's something else to consider. Now, scientists have used gravity and the mathematical formulas that they've created around gravity to find, well, I was about to say extraterrestrial objects, but not even extraterrestrial, but extrasolar, so outside of our solar system as well. Exoplanets is what we call them. Before the search for exoplanets, though, we needed to find all the planets in our solar system. And in the late 1700s, William Herschel was a British astronomer, and he was observing the movements of the stars and noticed that there was something odd about the movement of one, and that ended up being the planet Uranus. Later on, scientists were studying Uranus's orbit, and were seeing that it was kind of being pulled by another body, and it was determined that that must have been another planet. And when they finally triangulated where the location of that planet would be, they determined it was the planet Neptune. So these forces that cause Uranus to wobble slightly in its orbit is gravity, and it's the same force that causes Earth and other planets to revolve around the sun. So Sir Isaac Newton used known data about the solar system to describe the system of physical laws that govern the movement of celestial bodies around the sun, and he formulated what we call the universal law of gravitation. So this is Newton's universal law of gravitation, which I'd like you to copy down. There's an attraction between any two bodies if the objects have masses m1 and m2 and their centers are separated by a distance r. The magnitude of the gravitational force on either object is directly proportional to the product of m1 and m2 and inversely proportional to the square of r. So that's the universal law of gravitation. Basically, the force of gravity attracting two bodies together, the force on m1 to m2 is equal to the force on m2 to m1, so that Fg is the same. It's always pointing towards the other planet or the other mass, and it is proportional to the product of the masses and inversely proportional to the square of the distance between the masses. And this slide I'd like you to copy down as well. This is the universal law of gravitation written algebraically. Fg is equal to big G, which is a constant, and we'll get into that a bit later, times m1 times m2 over r squared. So the force of gravity is equal to this the product of the masses divided by the square of r, but also it's a product of the universal gravitational constant. And that value, which is on your formula sheet, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. What I would like you to do when you're doing any problems in this unit is to always use 3 significant digits for G, for big G, even if you have only 2 significant digits in your answer, or sorry, in your givens. This is because our big G is a fairly accurate measure, and we want to make sure that we don't lose too much information by rounding that to 6.7. With your little g, 9.8, if you have 2 significant digits, I recommend using 9.8 meters per second squared. If there are 3 significant digits in all the givens, use 9.81 meters per second squared. So one of the things we could also notice just by looking at this equation is that g itself is a very small number. It's of the order of 10 to the negative 11. That means that in order for a gravitational effect to be noticeable, the product of the masses has to be very large. So we have to have 2 large masses, and the distance between them has to be relatively short, because if we're dividing by an r squared, that means that our number is going to get smaller. So the bigger that r squared is, the smaller our overall force is. So this is you can calculate the gravitational force between you and another object, but even if you're very close to that object, the product of those masses is going to be very small compared to once you multiply by the 10 to the negative 11 order gravitational constant. So your force of gravity can be calculated, but it is going to be quite small. So next, we're going to try a problem out. This problem here says that we have a 65 kilogram astronaut who's walking on the surface of the moon. The surface of the moon, the moon has a radius of 1.74 times 10 to the 3 kilometers. The mass of the moon is 7.35 times 10 to the 22 kilograms. So what is the weight of the astronaut? So in this case, we need to find out what the Fg is. Weight is equal to the force of gravity. So let's quickly look over here. So we have Fg for this question. Sorry, I should put a lowercase g. Is our big G times our m1, m2 over r squared. And our G is 6.67 times 10 to the negative 11. That's our G value. Our astronaut is 65 kilograms. The weight of our moon is 7.35 times 10 to the 22. And our r squared, this is in kilometers. 1.74 times 10 to the 6 meters squared. Now remember that km means that we'd have to multiply by another 10 to the power of 3. So that gives us 10 to the power of 6. So 6.67 times 10 to the power of negative 11 times 65 times 7.35 times 10 to the power of 22 is our numerator. And I'll just write that down. It's going to be a very large number. Now we have to divide it by another very large number, which is 1.74 times 10 to the power of 6 squared. So we're left with 105. We were given 3 significant digits in every given here because it was 65.0, 7.35, 1.74. So here we write down our 3 significant digits, 105 newtons. Looking back at another problem, it says in an experiment, an 8 kilogram lead sphere is brought close to a 1.5 kilogram mass. The gravitational force between them is 1.28 times 10 to the negative 8 newtons, very small. It says how far are the centers of the objects. So in this case, we have to solve for r. So looking at this equation here, I have to rearrange that for r, which is the square root of g m1 m2 over fg. So in this case, 6.67 times 10 to the negative 11. M1, these are 2 small masses. They were 8 and 1.5. And it was 8.0. So we're going to have 2 significant digits in our answer. Our force is 1.28 times 10 to the negative 8. And when I evaluate this, I'm going to have, let's see, 6.67 times 10 to the negative 11. And I have to multiply that by 8, multiply that by 1.5, divided by 1.28, and 10 to the power of negative 8. Close my bracket, and then I would find the square root of this. I get 0.25. And I have to report this for 2 significant digits, so it's just 0.25, not 0.250. One more problem here. It says the radius of the planet Uranus is 4.3 times the radius of Earth. The mass of Uranus is 14.7 times the mass of Earth. How does the gravitational force on the surface of Uranus compare to that on Earth? So here, what I need to do for this problem is I need to look at this from, I have to compare my 2 FGs. So basically what I'm doing is I have an FG for Earth. I'll put FG with an E. And that's going to be G. My mass, the mass of Uranus is 14.7 times that of the mass of Earth. Actually, sorry, I shouldn't be doing this with the mass of Earth. I don't really need that. So my FG for Uranus would be my FG for Earth, or rather, my G is going to stay the same. My M is going to be 14.7 times the mass of Earth. and my radius is going to be 4.3 times the radius of Earth squared. So what happens here is I'm interested to see what happens to these two values. So the rest of this was just the f of g, e. So my FGU is equal to 14.7 over 4.3 squared. The rest of these variables is my FG of E. So if I find out what 14.7 divided by 4.3 squared is, I end up with 0.795, and I have to round that for two significant digits because there's a 4-3 here. There's a two significant digit answer here. So it becomes 0.80 FGE. So, Newton's law of gravitation plays a key role in physics for two reasons. So first, he showed for the first time that the laws of physics apply to all objects. The same force that causes a leaf to fall from a tree also keeps planets in orbit around the sun. The fact had a profound effect on how people viewed the universe. He also showed that the law, this law provided us with an equation to calculate and understand the motions of a wide variety of celestial objects, including planets, moons, and comets. So I'd like you to copy this down. There will be some more explain questions in this unit than you've seen in the previous units, so it's important to understand more of the underlying effect of the physics for these kind of discoveries that we'll see. Now the value of G, we write down 9.8 or 9.81 quite regularly, but in actuality that value of G that we calculate, little g I'm talking about, is dependent on how far you are from the center of the Earth. Now, on the Earth's surface, the value of G is approximately 9.8. The closer you are to, or if you are on a mountain, for example, the farther you are from the sea level, the higher that, or the lower that value of G will be. If you would go into a valley, you would have a higher G. There are places on the Earth that have higher or lower elevation. That would affect the value of G. One of the famous examples was when they had the Olympics in Mexico City. Certain sports that were dependent on the gravitational effect, like pole jumping and long jumping, records were broken because of the lower G value, because Mexico City is a relatively high altitude compared to places where other athletics events are held. Now that big G is actually quite interesting because it took quite a bit of time to calculate this, and it took an ingenious experiment that was developed by Henry Cavendish. He was a famous scientist, and he lived in the time shortly after Newton. So Isaac Newton theorized about this universal gravitational constant. Henry Cavendish was the one who ended up experimentally determining the value of G and thereby proving the existence of G. And he did this using an experiment that uses what's called a torsion balance. So I'll get into what this means, and I'd like you to copy this image down and the explanation of this experiment. So what Cavendish did was he used a torsion balance, and what a torsion balance is that it's a device where we have two objects affixed on a kind of an upside down T shape. and those two objects are brought near two other objects. So in that image, what you see are the two small spheres. Those are labeled M1, and the two large spheres that are labeled M2. So those small spheres they're fixed to each other. And if there is a force of gravity between all objects, then what we would see is that if we placed these small spheres near the two large spheres, there would be a little bit of a displacement between them. And using trigonometry, we would be able to calculate an angle of displacement. And then using trigonometry, we would be able to calculate what force is causing that displacement. So we would know what the distance between the centers are. We would know the angle. And then we can find out what force is causing it to displace at that distance r. So basically, this mass bar system rotates. What Cavendish ended up doing was he used a light source to measure that angle. He pointed it at a mirror and then measured the angle. He had to do this experiment very far away from where this was occurring in order to reduce the amount of gravitational effects caused by his body or by other large masses that might have been present. So this was a very delicate experiment, and it's an experiment that has been replicated a number of times, and it was shown, and it still has been shown, to find a fairly accurate measure for the value of big G. Now we can actually do this experiment with smaller and smaller torsion balances and get more and more accurate values for G. So that explains the experiment. So copy down that slide 13 and 14. Copy the image down as well. If you need any extra help, you can actually look online. This experiment's explained quite regularly on the internet and at other sources. But your textbook also goes through a nice explanation as well. You'll need to understand how that works. And I'll want you to copy this down as well. The universal gravitational constant, G, was determined experimentally by Cavendish. He used a torsion balance to measure it. You should also say that it was first theorized by Isaac Newton. There were a few others as well, but Newton would be one of the most famous ones. Here's another problem. It says Eros, a dwarf planet, is the 9th most massive body orbiting the Sun. It's more massive than Pluto and 3 times farther away from the Sun. Eros is estimated to have a radius of approximately 1,200 kilometers. Suppose an astronaut stands on Eros and drops a rock from a height of 0.3 meters. The rock takes 0.87 seconds to reach the surface. Calculate the value of G on Eros. So what we'll do here is we need to find out what our little g is. And we actually have to go back to our kinematics problems, because what we have is a d of 0.3 meters. We have a t of 0.87 seconds. What's not given to us, but what is implied, is that our VI is 0 meters per second. And what we need to find is our A, which is our G for Eros. I should capitalize that. So dTV, what I can do is I can use my equations from the kinematics unit, or rather from the dynamics unit, but the kinematics section of that unit. What I'm looking for is what is my A, and I know that I can use D equals VIT plus AT squared over 2. This is 0. D is 0.3. A, I'm going to rewrite it as G over 2. T is 0.87 squared. Sorry, I should actually rearrange this. 0.3 over 0.87 squared, so that we're only doing this once in our calculator. 2 times 0.3 divided by 0.87 squared. I get 0.79 meters per second squared. The second part of this problem asks us to calculate the mass of Eros. So this is rather interesting. With that simple calculation of G, we can calculate the mass. So now that I've calculated my G for Eros, I have two FG equations. So I have my force of gravity, which is G times the mass of the rock times the mass of Eros over the radius of Eros squared. That Fg is going to be equal to this Fg, which is the mass of the rock times the G that we've calculated here. So what I could do is, I don't know the mass of my rock. So I could make these two equal, and you'll see that I can actually cancel out the mass of my rock. So Mr G Eros is equal to G Mr M of Eros over R of Eros squared. I'm going to rearrange this to solve for M of Eros, but my Mr can be divided on both sides, so that makes this a lot simpler. My M of Eros that I need to calculate then is the G of Eros times the R of Eros squared over my big G. So this becomes 0.79, although I'm going to put in the exact value that I have here. I still have it in my calculator as 0.792707. My mass of Eros, which was given to me in kilometers, so I'm going to write it as 1200, and then put 3 more zeros after it because it's in kilometers. G is 6.67 times 10 to the negative 11. So using that, I can then calculate. So this is my G times 1200,000 squared divided by 6.67 divided by 10 to the power of negative 11. That gives me a mass of Eros of 17 something, and then there's a bunch of numbers. I don't even know what this number is. But what I'm going to do is I'm going to change it to scientific notation. I had, back in my problem, I had a limitation of 0.30 and 0.87 seconds. So my mass of Eros can only be accurate up to 2 significant digits. So 1.7 times 10 to the power of 22 kilograms would be my mass of Eros. So from a simple simple experiment of dropping an object onto the floor, you can calculate the mass of the body on which you're standing. So you can do this with the mass of Earth, and you'll get fairly accurate answers if you've measured it with good accuracy. Now, you'll see this problem again with other planets, so just make sure you know how to do this. One of the common problems I get is, how do I solve this if I don't have the mass of the rock or the object that falls? You don't need it. You can cancel it out just as we've done here. Okay, going back to the presentation, we're almost done. So we can do calculations in 3 space as well. And here's an example of a, this is 2-dimensional, of a 2-dimensional problem that involves the force of gravity. So this will take a bit of time to do, but this is a good question to solve. So let me just explain it first, and then we'll start the solution. So we have 3 large spherical asteroids. They're arranged A, B, C. These 3 objects can be thought of in a single plane. Object A is the smallest one. It is 1 times 10 to the 20 kilograms. Object B is double that size, and object C is double the size of B. and 4 times the size of A. The distance between them is listed as well. We need to find the net force on asteroid A due to asteroids B and C. Now, just looking at the problem, we know that B is going to be attracted towards A, and B is also going to be attracted towards C. So B would be moving down and to the right. We know that C is attracted to A and B, so it will be moving left and up. A would be moving up and to the right. So gravity is always an attractive force, so that means that the forces are always going to be moving inward for a three-body problem like this. So for a problem that's going to involve two-dimensional space, well, we're going to have, in this case, two FGs to calculate. So we have our FG between A and B and our FG between A and C. So this is the force that A is experiencing due to B. So if you remember from our image, A was below B, so that means A is going to be moving up. And this is the force that A is experiencing due to C. So this, because A was on the left of C, FAC is going to be going to the right. I don't have to include these directions each time. I'm just doing that to show you. Now, these are two separate calculations, so I'll do them separately, but they are essentially the same type of calculation. So our mass of A, which is 1 times 10 to the 22, our mass of B, which is 2 times 10 to the 22, or sorry, I think it was just to the 20, yeah. Over our RAB, which was, in this case, 5 times 10 to the 10 squared. On this side here, I ran out of space a little bit, 6.67 times 10 to the negative 11. 1 times 10 to the 20. 4 times 10 to the 20. Over the distance here, which is 2.5 times 10 to the 10. Oops. So calculating these each, we're going to have 6.67 times 10 to the power of negative 11. One thing I'm going to show you actually, because I use this constant so often, I'm going to save it into my memory. So anytime I need it, I can just store it. You can do this on your calculator, and your calculator is much better in the sense that you probably have multiple spots to save constants. So that is now stored in memory. That G value times 1 times 10 to the power of 20 times 2 times 10 to the power of 20 divided by 5 squared divided by 10 to the power of 10 squared. So 10 to the power of 10 squared equals this value, which ends up being 5.3 times 10 to the power of 8 newtons up. Now the next, or rather, I have to do this again. So going back here, I can recall my G times 1 times 10 to the power of 20 times 4 times 10 to the power of 20 divided by 2.5 squared and divided by 10 to the power of 10 squared, which is the same as 10 to the power of 20. I end up with 4.3 because of two significant digits times 10 to the power of 9. That's newtons to the right. So what I'm going to do is to find out what my F A is for both of these. It's going to be the square root of FAB squared plus FAC squared. and that's going to be the square root of 5.336 times 10 to the 8 squared plus 4.2688 times 10 to the 9 squared. I'll have to find the angle as well. So the angle is going to be, I like to always have it less than 45 degrees. So that means I'll take the smaller of the two, which is the 5.3, inverse tangent first of 5.336 times 10 to the 8 divided by 4.2688 times 10 to the power of 9. So that's going to be my angle calculation. Let's do this here. So I have this value already in here, so I'll square this. I will add to that 5.336 times 10 to the power of 8. I'll do the power of 16, and I'll multiply by 5.336 again, just because I kind of screwed up the squaring part. That gives me this value, and I find the square root of that. I end up with 4.3 after I round times 10 to the power of 9 newtons. I now have to find out the direction, which is over here. So my angle is going to be 5.336 times 10 to the power of 8 divided by 4.2688 divided by 10 to the power of 9. So this value, inverse tangent of that, gets me to 7.125 degrees. And your degree measure should always just be in terms of degrees, whole degrees, unless you're told to do something separately, or unless we're dealing with very small angle measures like we'll be dealing with in Unit 4. So in this case, with your degrees, you don't necessarily round to your significant digits. You round to the wholest degree, unless you're given more accurate information or other information. So if that's 7 degrees, that means that my direction is, this would be going more towards the greater value, which is to the right. So it would be 7 degrees, or so it would be right, 7 degrees up. And that is my solution for that 3-body gravity problem. Newton's law of universal gravitation has stood the test of time and extended the limits of space. So as far into space as astronomers can observe, celestial bodies move according to Newton's law. As well, astronauts of the crippled Apollo 13 spacecraft owe their lives to the dependability and predictability of the moon's gravity. So we've tested Newtonian gravity time and time again, and it works very well. We're very confident in that FG equation. So although Albert Einstein took a different approach in describing gravity in his general theory of relativity, most calculations that need to be made can use Newton's law of universal gravitation and make accurate predictions. When we get into relativity, things get a little bit more complicated. So for our purposes, in this unit, we're going to use FG, the equation FG equals G times the product of the masses over the square of the distance between them. In your later courses, you might be introduced to some other ways of calculating that, but the Newtonian gravity, that law of universal gravitation, works very well for what we are doing in this course.